What if I told you that the fundamental rules of building, well, everything, just got rewritten? Forget everything you thought you knew about the limits of strength and weight. Imagine holding a block of material that feels lighter than a piece of styrofoam in your hand, yet possesses the raw strength to potentially stop a bullet or form the backbone of a spaceship destined for Mars. Sounds like pure science fiction, right? Like something ripped from a futuristic movie. Well, buckle up, because that future isn't decades away, it's unfolding right now. Scientists, armed with the power of artificial intelligence and the precision of 3D printing, have just cracked a code that has baffled engineers for centuries, creating a nanomaterial that doesn't just push the boundaries, it completely obliterates them. We're talking about a substance 5 times stronger than titanium, the gold standard for aerospace, while being almost impossibly light. Think about that for a second. What could we build? How would our world change? And the most mind-bending part, it wasn't designed by human intuition alone. It was dreamed up by an AI. How did a machine conjure a material stronger than anything nature or human ingenuity has produced before? And what does this mean for you? Stick around, because this story isn't just about science. It's about the dawn of a new material age. For as long as humans have been building things, from the first mud huts to soaring skyscrapers and interplanetary rockets, we've faced a fundamental, frustrating trade-off. It's the engineer's eternal headache: strength versus weight. You want something incredibly strong, something that can withstand immense forces, resist shattering, and hold its shape under extreme stress. You typically reach for materials like steel or titanium. Think about the massive steel beams holding up bridges, the thick hulls of warships, or the robust engine components in a jet. They do the job, they're reliable, but boy, are they heavy. Every pound of steel in a car means more fuel burned. Every kilogram of titanium on a rocket means exponentially more propellant needed just to lift it off the ground. It's a constant battle against gravity and inertia. Now, on the other side of the spectrum, you have materials prized for their lightness. Think carbon fiber composites used in racing bikes and high-performance aircraft skins, or even common styrofoam used for packaging. They're incredibly light, sometimes almost ethereal. Carbon fiber offers fantastic strength for its weight in specific applications, but it can be brittle and expensive. Styrofoam, great for cushioning your new TV, but you wouldn't build a bridge out of it. It's fragile, easily crushed, and certainly not up for heavy-duty tasks. This dilemma has defined the limits of our engineering ambitions. How high can we build? How fast can we fly? How efficient can our vehicles be? All these questions bump up against the physical limitations imposed by the strength-to-weight ratio of available materials. For decades, scientists have chipped away at this problem, creating alloys, composites, and clever structural designs to find a better balance. One promising avenue has been the realm of nano-architected materials. This isn't about discovering a new element. It's about taking existing materials and engineering their structure at an incredibly tiny scale. The nanoscale, think billionths of a meter. Imagine building with microscopic Lego bricks, creating intricate, repeating patterns like tiny lattices or trusses. The idea is that by carefully designing this microarchitecture, you can achieve properties impossible in the bulk material. You can make something porous like a sponge, but with a structure designed for strength, resulting in materials that are both strong and lightweight compared to their solid counterparts. It sounds perfect, right? The best of both worlds. Well, there's been a persistent snag. Many of these early nano-architected materials, while impressive in strength-to-weight tests, had an Achilles heel: brittleness. They could withstand significant force, holding strong right up until snap. They'd fail suddenly and catastrophically, shattering like glass rather than bending or deforming like metal. Imagine a bridge support that seems perfectly fine one moment and explodes into dust the next under load. Not exactly reassuring for critical applications. This brittleness limited their practical use, keeping them largely confined to labs. Finding that magic combination, ultra-strong, ultralight, and tough, meaning resistant to fracture, remained elusive. Human designers, relying on established engineering principles and intuition honed over centuries, kept hitting this wall. We needed a new approach, a way to explore design possibilities far beyond what our own minds could conceive. And that's precisely where artificial intelligence enters the picture, not just as a tool, but as a creative partner. Researchers, particularly brilliant minds at Caltech and the University of Toronto, looked at this brittleness problem and realized that traditional design methods, even computer-aided ones guided by humans, were essentially exploring variations on known themes. They were trapped within the box of human understanding of structural mechanics. What if, they pondered, there were entirely alien geometries, counterintuitive structures that could distribute stress in ways we'd never imagined? Instead of trying to iteratively improve existing designs, they decided to let a machine learning algorithm loose on the problem. Think of it like this. They didn't just give the AI a library of existing successful and unsuccessful designs. They essentially gave it the fundamental rules of physics and material properties and tasked it with generating and testing thousands upon thousands of potential nanolattice designs, microscopic frameworks of interconnected struts and nodes. The AI wasn't just pattern matching or tweaking known shapes. It was performing a high-speed virtual simulation of evolution. It would generate a design, simulate how stress flowed through it under load, analyze its strength, its weight, and critically, its failure points. It learned which geometric features led to strength, which led to lightness, and crucially, which configurations avoided the stress concentrations that cause brittle fracture. It started predicting entirely new geometries, shapes that looked, well, frankly, weird. Structures that a human engineer, bound by conventional wisdom, might have dismissed as nonsensical or impossible to fabricate. These weren't just slight variations. They were fundamentally different ways of arranging matter at the nanoscale. The AI model wasn't burdened by preconceived notions or aesthetic preferences. It only cared about the numbers: maximize strength, minimize weight, maximize toughness. It explored a vast, multi-dimensional design space far faster and more comprehensively than any team of humans ever could. It could identify subtle interactions between geometric features that would be invisible to the naked eye or even standard analysis software. The result of this AI-driven exploration wasn't just an incremental improvement. It was a leap. The AI pinpointed a novel nanolattice structure that, when fabricated, displayed properties that shattered existing records. A material with the predicted characteristics, 5 times stronger than titanium, a benchmark material in demanding fields like aerospace and medical implants, while being significantly lighter. This wasn't just optimizing. This was true design discovery, facilitated by machine intelligence. It proved that AI could not only analyze complex problems, but could generate genuinely novel solutions to one of the oldest challenges in material science. So, how does this miracle material actually work? What's the secret sauce behind its incredible properties? It boils down to that term we mentioned, nanolattice. But let's unpack that, because the elegance is in the details. First, why nano? We live in a world built from materials we can see and touch: steel girders, wooden planks, plastic casings. But when you want to fundamentally change the properties of a material, sometimes you need to manipulate its structure at the smallest possible scales. We're talking nanometers, billionths of a meter. To put that in perspective, a single human hair is about 80,000 to 100,000 nanometers wide. Nanomaterials are engineered at this incredibly fine level. You already encounter them, perhaps without realizing it, in sunscreens, titanium dioxide nanoparticles, advanced electronics, quantum dots, and even some medical treatments. Their small size gives them unique properties, like a vastly increased surface area to volume ratio, which can dramatically alter chemical reactivity or, in this case, structural performance. Now imagine taking a material, It could be a ceramic, a metal, or even a polymer. And instead of using it as a solid block, you use it to build an intricate, three-dimensional repeating framework, like microscopic scaffolding. That's the nanolattice. It's composed of tiny beams called struts, connected at points called nodes. Think of the Eiffel Tower, but shrunk down billions of times and repeated over and over in 3 dimensions. Or perhaps a more organic analogy. Think of the internal structure of bone, which uses a porous, lattice-like architecture, trabecular bone, to achieve strength and resilience without being a solid, heavy mass. The genius of the AI-designed nanolattice lies in the precise geometry of these struts and nodes. Traditional materials often fail because stress concentrates at tiny imperfections or specific points within the material. Imagine putting pressure on a solid block with a small crack in it. The stress flows towards the tip of that crack, amplifying it until the material breaks. The AI-designed lattice, however, acts like a sophisticated network for distributing stress. When a force is applied, it doesn't concentrate in one area. Instead, the load is shared efficiently across the interconnected network of struts. Each tiny beam takes a small portion of the load, preventing any single point from becoming overloaded. This intricate stress distribution prevents weak points from forming and propagating, which is the key to avoiding the sudden, brittle failure seen in earlier designs. The AI found a geometric arrangement that is exceptionally good at dissipating energy and spreading out forces. Okay, so the AI designed this amazing blueprint. But how do you actually build something so mind-bogglingly small and precise? You can't exactly use tiny welders and cranes. This is where advanced 3D printing, often called additive manufacturing, comes in, but operating at the nanoscale. Techniques like two-photon lithography allow scientists to essentially draw these intricate 3D structures layer by microscopic layer using highly focused lasers on a special light-sensitive resin. The laser solidifies the resin only at the precise points needed to build the lattice, washing away the unused material afterwards. This allows for the creation of incredibly complex geometries with nanoscale features, turning the AI's digital blueprint into a physical reality. The final product, a material boasting a specific strength divided by density that is off the charts. The researchers measured a stress tolerance, the amount of force it can handle before failing that, when adjusted for its incredibly low density, comes out to be 5 times greater than that of high-grade titanium alloys. That figure, 2.03 megapascals per cubic meter per kilogram, might sound abstract, but let's translate it. Remember that airplane example. Replacing titanium components with this material could save roughly 80 liters of jet fuel per kilogram replaced per year. Now, multiply that by the hundreds or thousands of kilograms of titanium potentially used in a large aircraft, and then multiply that across an entire airline fleet operating for years. We're not talking about shaving off a tiny percentage. We're talking about potentially saving millions of liters of fuel, drastically cutting operational costs and greenhouse gas emissions. That's not just an improvement, it's a paradigm shift. And perhaps just as importantly, remember the brittleness problem. The AI design cracked that too. This material isn't just strong, it's remarkably resilient. Unlike those earlier nano-architected materials that shattered catastrophically, this structure exhibits more toughness. It can withstand extreme stress without suddenly disintegrating. This resilience opens the door to applications where sudden failure is simply not an option. Think critical aerospace components, protective armor, or even medical implants that need to last a lifetime. We are looking at a material that combines the previously incompatible virtues of extreme strength, extreme lightness, and impressive toughness, all thanks to an AI's unconventional design insight. Okay, let's zoom out from the lab and talk about the real world. A material lighter than foam but stronger than steel. This isn't just a scientific curiosity. It's a potential catalyst for transformation across industries that shape our modern lives. The ability to decouple strength from weight unlocks possibilities that were previously confined to the realm of science fiction. So, how exactly could this AI-designed supermaterial reshape our world? Let's break it down. First, consider aerospace and space exploration. This is arguably the most immediate and impactful area. Weight is the absolute enemy in anything that flies. Every single kilogram launched into orbit costs thousands of dollars. Every extra pound on an airplane increases fuel burn minute by minute. Imagine replacing significant portions of an aircraft structure, wing components, fuselage sections, landing gear, currently made from titanium or aluminum alloys, with this new material. Airplanes could become dramatically lighter. This translates directly to massive fuel savings, reducing operating costs for airlines and significantly lowering the environmental impact of air travel. We're talking potentially longer ranges, allowing for non-stop flights on routes previously impossible, or the ability to carry more passengers or cargo with the same amount of fuel. For space exploration, the benefits are even more profound. Think about NASA's Artemis program aiming for the Moon and Mars, or SpaceX's Starship ambitions. Lighter spacecraft mean less powerful, less expensive rockets are needed to launch them. Or alternatively, the same rocket can carry much more scientific equipment, supplies, or even habitat modules. Satellites could become lighter, making launches cheaper and potentially extending their operational lifespan by allowing more fuel for station keeping. Drones and helicopters could see huge gains in flight time, maneuverability, and payload capacity, revolutionizing everything from package delivery and agricultural monitoring to aerial surveillance and emergency response. The very economics and feasibility of operating in the air and in space could fundamentally change. Now, let's bring it down to earth and look at the automotive industry. Weight reduction is the holy grail here too, especially with the shift towards electric vehicles, EVs. One of the biggest hurdles for EVs is range anxiety, the fear of running out of charge. Lighter vehicles require less energy to move. Integrating this AI-designed material into car frames, battery casings, and other structural components could lead to EVs that travel significantly farther on a single charge, making them more practical and appealing to a wider audience. Performance could improve too. Lighter cars accelerate faster and handle better. But it's not just about efficiency, it's also about safety. Stronger materials mean safer cars. Manufacturers could reinforce critical areas of the vehicle's structure, the passenger safety cell, crumple zones, to provide much better crash protection without adding the significant weight penalty that usually comes with reinforcing steel structures. Imagine cars that are both lighter and significantly safer in a collision. Furthermore, as 3D printing technology matures, it could potentially lower manufacturing costs for complex parts made from this material, eventually making these benefits accessible beyond just high-end luxury or performance vehicles. Let's turn to military and defense. For soldiers on the ground, survivability and mobility are paramount. Current body armor often involves heavy ceramic plates, effective but cumbersome. This high-strength, low-weight material is ideal for next-generation body armor and helmets. It could offer superior protection against projectiles and shrapnel while being significantly lighter, reducing fatigue and improving agility for soldiers in combat zones. Think about the difference that shedding several pounds of armor could make over a long patrol. Armored vehicles could also benefit immensely. Lighter armor means vehicles could be faster, more fuel-efficient, more easily transportable by air, and potentially more survivable as the same level of protection could be achieved with less mass. Drones built with this material could fly longer, farther, and be more resilient to damage, enhancing reconnaissance, surveillance, and tactical capabilities. And it doesn't stop there. Think about consumer electronics and everyday technology. How many times have you cringed watching your smartphone tumble towards the pavement? The strength and potential flexibility of AI-designed nanomaterials could lead to lighter, more durable phones, laptops, and tablets. Imagine screens that are virtually shatterproof or casings that resist dents and scratches far better than current materials. Wearable technology, smartwatches, fitness trackers, augmented reality glasses could become not only lighter and more comfortable but also far more robust, capable of withstanding the bumps and scrapes of daily life. Even batteries could benefit. While the chemistry inside is key, the casing adds weight. Stronger, lighter casing materials could contribute to overall weight reduction in portable electronics and EVs, enhancing efficiency. These are just the obvious starting points. The potential applications ripple outwards: stronger, lighter sporting goods, more durable medical implants, revolutionary construction materials for specific high-stress applications. We are truly just scratching the surface of what becomes possible when you fundamentally change the rules of material properties. This breakthrough isn't just about discovering one single supermaterial. It's much bigger than that. It represents a fundamental shift in how we discover and design materials. We've entered an era where artificial intelligence is acting as a powerful collaborator, capable of navigating complexity and uncovering solutions that lie far outside the bounds of human intuition. For centuries, material discovery was a slow process, often relying on painstaking trial and error, accidental discoveries, or incremental improvements based on existing knowledge. Scientists would mix elements, test properties, tweak formulas, a process that could take years, even decades, to yield significant results. AI changes the game entirely. By feeding algorithms vast datasets of material properties, chemical compositions, and structural configurations, and combining that with physics-based simulations, AI can predict the properties of hypothetical materials with astonishing speed and accuracy. It can optimize structures for multiple objectives simultaneously: strength, weight, conductivity, flexibility, resistance to heat or corrosion, in ways that are incredibly challenging for human designers. It's like having a tireless, brilliant researcher who can explore millions of possibilities overnight. The success with this nanolattice material is proof of concept. AI has demonstrated its ability to engineer structures that humans likely would never have conceived on their own, unlocking performance levels previously thought impossible. This accelerates the pace of innovation dramatically. Problems that might have taken decades to solve through traditional methods could potentially be cracked in months or years. The immediate next challenge, of course, is scaling this technology. Right now, creating these intricate nanolattices using techniques like two-photon lithography is a highly precise, relatively slow and expensive process, suitable for lab research or perhaps very high-value, small-scale applications. The hurdle is transitioning from creating tiny samples under a microscope to producing sheets, beams, or complex components at an industrial scale, quickly and cost-effectively. Scientists and engineers are already hard at work on this, exploring faster 3D printing techniques, alternative manufacturing methods, and ways to optimize the process for mass production. If they succeed, and the history of technology suggests they eventually will, AI-designed materials could become the bedrock of a new industrial revolution, impacting virtually every sector. And this truly is just the beginning. AI isn't just optimizing existing material types. It's paving the way for entirely new classes of materials with functionalities straight out of science fiction. Imagine ultra-thin, flexible, yet virtually indestructible phone screens. Forget Gorilla Glass. Think about a screen made from an AI-designed nanomaterial that can bend, flex, and absorb impacts without cracking or shattering, no matter how many times you drop your device. AI could design materials that combine transparency, conductivity, for touch sensitivity, flexibility, and extreme toughness in ways current materials can't. Or consider the fascinating field of self-healing materials. Scientists are using AI to design materials with embedded microcapsules containing repair agents, or materials whose intrinsic chemistry allows them to mend themselves when damaged, much like biological tissue regenerates after a cut. Imagine an airplane wing that can automatically repair minor cracks sustained during flight, or a car's paint job that fixes scratches on its own, or bridge supports that counteract microscopic fatigue damage over time. This could drastically reduce maintenance costs, improve safety, and extend the lifespan of critical infrastructure and products. Perhaps the most ambitious frontier is in space-age construction. Building habitats on the Moon or Mars presents extreme challenges: massive temperature swings, hard vacuum, intense radiation, and the prohibitive cost of launching materials from Earth. AI is being explored to design materials that are not only ultralight and super strong, but also inherently resistant to radiation, capable of being manufactured in situ, using local resources on the Moon or Mars, and tailored for the specific demands of extraterrestrial construction. Organizations like NASA and SpaceX are actively investigating how AI-driven material discovery can provide the foundational materials needed for humanity's future off-world. These examples, indestructible screens, self-healing structures, space-ready materials, highlight the transformative potential. AI is not just finding stronger, lighter versions of what we already have. It's enabling the creation of materials with entirely new, programmable functionalities, pushing the boundaries of what matter itself can do. Now, amidst all this excitement and futuristic possibility, it's crucial to inject a dose of realism. While the potential of AI-designed materials is undeniably enormous, there are significant hurdles to overcome before you're flying in a plane made of this stuff or carrying a self-healing phone. The path from a lab breakthrough to widespread, everyday use is often long and challenging. The first major obstacle, as we touched upon, is scaling up production. Manufacturing materials with features measured in nanometers requires extraordinary precision. The current 3D printing methods, while capable of creating these intricate structures, are generally slow and operate on a small scale. Think about the difference between meticulously crafting a single, exquisite-scale model versus mass-producing thousands of full-size cars on an assembly line. We need breakthroughs in manufacturing technology to produce these nanomaterials quickly, reliably, and in large enough quantities for industrial use. Until we can bridge this gap from lab-scale fabrication to cost-effective mass manufacturing, the use of these materials will likely be limited to specialized, high-value applications where cost is less of a concern. Think Formula One racing, high-end military gear, or critical components on spacecraft. Related directly to scaling is cost. Advanced materials are almost always expensive when they first emerge. Titanium was once considered an exotic and costly material. Carbon fiber composites still are, compared to steel or aluminum. The complex manufacturing processes, specialized equipment, and potentially expensive raw materials involved in creating AI-designed nanomaterials mean they will initially carry a hefty price tag. While costs inevitably decrease over time as technology matures, production scales up, and competition increases. Think how the cost of computing power has plummeted. The initial high cost will be a significant barrier to widespread adoption, especially in cost-sensitive industries like mass-market automotive or consumer goods. Then there's the challenge of industry adoption. Even if the material becomes manufacturable at scale and the cost comes down, large industries don't just switch materials overnight. Companies have established supply chains, manufacturing processes, and design philosophies built around traditional materials like steel, aluminum, and plastics. Integrating a radically new material requires significant investment in research and development, retooling factories, retraining workforces, and redesigning products to take full advantage of the new material's properties. Engineers need time to thoroughly test and validate these materials under real-world conditions, subjecting them to stress, fatigue, environmental exposure, and various failure scenarios, to build confidence in their long-term reliability and performance. This validation process takes time and resources. Finally, and critically, there's regulatory approval. In sectors like aerospace, automotive, medical devices, and military applications, safety is non-negotiable. Materials used in aircraft structures, car safety cages, or implantable medical devices must meet incredibly stringent safety standards and undergo rigorous, often years-long testing and certification processes mandated by regulatory bodies like the FAA or FDA. Even a minor change in material composition can trigger a lengthy and expensive recertification process. Replacing fundamental structural materials like steel or titanium with a completely novel AI-designed nanomaterial will require extensive data demonstrating its safety, durability, and predictable performance under all conceivable operating conditions. This regulatory hurdle is perhaps one of the most significant, ensuring that adoption, especially in safety-critical applications, will be gradual and cautious, likely taking place over the next decade or more. Despite these substantial hurdles, the momentum behind AI-driven material science is undeniable. The potential benefits are simply too large to ignore. As AI algorithms become more sophisticated, manufacturing techniques improve, and our understanding of nanoscale engineering deepens, these challenges will be addressed. The question isn't really if these materials will change the world, but how quickly we can overcome the obstacles to unlock their full potential. So here we stand, at the cusp of what could genuinely be called a new material age. AI is not just analyzing data anymore. It's becoming a creative force, designing matter itself in ways that defy our intuition and shatter long-held limitations. We're looking at a future where the fundamental trade-offs that have governed engineering for millennia, strength versus weight, durability versus flexibility, might become things of the past. Imagine skyscrapers that reach even greater heights, built with materials possessing the strength of steel but a fraction of the weight. Picture aircraft that sip fuel, making travel cleaner and potentially faster. Envision cars that cocoon passengers in ultra-strong safety cages without sacrificing efficiency. Think of space exploration becoming more feasible, more sustainable, driven by lighter, more resilient spacecraft. The possibilities sparked by AI designing materials stronger than titanium and lighter than foam are truly mind-boggling, stretching the limits of our imagination. It forces us to reconsider what's possible in nearly every field of human endeavor. But this story leaves us with some profound questions. How quickly can our industries adapt and integrate these revolutionary materials? Will the cost ever come down enough for them to become commonplace, or will they remain the preserve of high-tech, high-cost applications? And perhaps most importantly, as AI continues to accelerate discovery, what other impossible materials lie just over the horizon, waiting to be conceived by a non-human intelligence? What happens when AI starts designing materials with properties we haven't even thought to ask for yet? For me, the lesson here is about the incredible power of new tools and new ways of thinking. AI isn't replacing human ingenuity, it's amplifying it, allowing us to tackle problems from entirely new angles and reach solutions previously inaccessible. It's a reminder that the limits we perceive are often based on our current understanding and tools, and breakthroughs can come from unexpected places. My advice, drawn from this incredible story: stay curious, Pay attention to these technological convergences: AI, nanotechnology, advanced manufacturing. They are not isolated developments. They are interacting and amplifying each other, creating possibilities that will reshape our world in profound ways. Think about how these advancements might impact your own life, your career, your community. Embracing change and understanding the forces driving it is key to navigating the future. What do you think? Are you excited about the potential of these AI-designed supermaterials? Which application excites you the most? Or do the challenges of scaling and cost make you skeptical about seeing them anytime soon? Let me know your thoughts in the comments below. I'm really curious to hear your perspective. Thank you so much for joining me on this journey into the future of materials. I hope you found it as fascinating as I do. Wishing you all good health and a future filled with wonder and innovation. If you enjoyed this exploration and want to stay updated on more groundbreaking science and technology stories, please hit that subscribe button and turn on notifications. Your support helps us bring these incredible advancements to light. Until next time, keep questioning, keep learning, and keep imagining what's possible.